Okay, let's unpack this. You know binary search, right?
Oh, yeah, absolutely. It's that fundamental algorithm.
The one we all learn, like the standard way to find something super fast in a list that's already sorted.
Mm-hmm. Like flipping through a dictionary, right? You jump to the middle, then halfway again.
Exactly, until you zero right in. It's incredibly efficient.
It really is.
But here's the thing. Binary search isn't only about finding if something's there. What if you have this nice, neat, sorted list,
Uh-huh.
and you need to stick a new item into it, but you have to keep it perfectly sorted. You can't just tack it on the end.
Right. You need to maintain that order. That's crucial.
And it turns out binary search has some really clever variations just for finding that perfect insertion spot.
And that's exactly where we're diving deep today. We're looking at using these binary search techniques specifically to find the insertion index, the right place for a new element in a sorted array.
We'll look at the simple case first, where all the elements are unique.
Yeah, no duplicates to worry about initially,
Yeah,
and then we'll get into the trickier situation where duplicates are allowed.
got it. And for this deep dive, our guide is some material from Hello Algo. They've got a great section on binary search insertion that lays it all out.
Yeah, it's a really clear explanation. So our mission here really is to go beyond just, listing the steps.
Right.
We want you to walk away understanding the logic, why these binary search tweaks work so well for keeping things sorted efficiently.
And how small changes like handling duplicates affect the algorithm?
Exactly. So you don't just know the how, but the why. Hopefully you'll remember this core technique for, well, forever. It's that fundamental.
And why should you care? Well, think about it. Anytime you're working with sorted data,
Databases,
yeah, databases, search indexes, maybe keeping game leaderboards updated,
or even just, file systems.
you need to add new stuff all the time.
Yeah.
And you can't afford to just scan through the whole list every time. That's way too slow.
Definitely. Finding that insertion point fast is key to building efficient systems. It pops up everywhere.
Okay, so let's start with that first scenario from the source. A sorted array, everything in it is unique, no repeats.
Right. And you have a target value you want to insert, the
Yeah.
goal, put it in the right place so the array stays sorted.
And the source adds a specific rule for this unique case. If the target number you want to insert, if it's already in the array,
Uh-huh.
the new one goes immediately to the left of the existing one.
Okay, so it sort of bumps the existing one over.
Yeah, essentially taking its spot. So we need our algorithm to find the index where this insertion should happen.
Right. Which leads to two key questions the algorithm needs to answer based on that rule. First, if the target's already there, what's the insertion index?
Okay.
And second, if the target is not there, where does it go to keep things sorted?
All right, let's tackle the first one. Target's already there. Rule says insert the new one to its left. So the new element basically takes the index of the one that's already there. The old one and everything after it gets shifted right.
So the insertion point is simply the index of that existing element.
Exactly. The algorithm just needs to find that index and return it.
Okay. And this is where binary search comes in to find that index efficiently. We use the standard setup, 2 pointers, often called I and J.
Right, marking the start and end of our search space.
And the source uses a closed interval, IJ, meaning the elements at index I, A, and D, index J, are included in the search.
Initially, I is 0, J is the last index, and 1.
Correct. And we keep searching as long as I is less than or equal to J, standard binary search loop condition.
Inside that loop, we do the usual thing, calculate the middle index, M.
Yep, M is roughly I plus J2. Then you compare the element at numsism with your target.
Okay, comparison time. What are the possibilities?
Well, first, if numsism is less than the target.
Then the target, if it exists, must be further to the right.
Exactly. So we can completely ignore the left half of our current range, including the element at M. We do that by moving the left pointer I up to M plus 1.
Got it. Our new search space is M plus 1, J smaller.
Right. Now, the second case, if numism is greater than the target.
Okay, opposite situation. The target must be to the left.
Correct. So we discard the right half, again, including M. We move the right pointer J down to M1.
Makes sense. New space is I, M1.
Now, the third possibility in this unique element case, what if numism is equal to the target?
Ah, we found it. And because the rule says insert to the left of an existing element,
That means index M is our insertion point.
perfect. So we found it. We can just stop searching and return M.
Precisely.
So this loop keeps going, chopping the search space in half each time until one of two things happens.
Either we hit that numism target condition and return M right away,
Or
or the pointers cross.
Yep.
The loop condition is ij. When I eventually becomes greater than j, the loop stops.
And that happens when the target wasn't actually found in the array.
Exactly. And this is where it gets kind of cool for insertion. When that loop terminates, because ij, the pointer I, isn't just useless, it actually tells you something very important.
Okay. What does it tell you?
Think about how the pointer is moved. I always got pushed past elements that were less than the target.
Right. IOM+1 only happened if num-ism target.
And j always got pulled back past elements greater than the target.
Because j equals m1 happened if num-ism target.
So I is sort of like the lower bound moving rightwards past small numbers.
Yeah.
And j is the upper bound moving leftwards past large numbers. They're trying to zero in on the target spot.
Ah, okay. They're squeezing the potential location.
Exactly. When I finally crosses jij, that search space ij is effectively empty.
Right.
But I has landed precisely at the index where the target should be inserted to maintain the sorted order.
Wait, really? How does that work?
Because I start moving right just before it would have pointed to something greater than or equal to the target, it marks the boundary. It points to the first element in the remaining conceptual space that is not less than the target.
Wow. So even if the target isn't found, the process naturally guides that to the exact insertion slot.
That's the elegance of it. If the target was found, we return them earlier. If it wasn't found, the loop finishes and we return again.
So in both scenarios, target found or target not found, this modified binary search gives us the correct insertion index.
Correct. And it does it in O log n time. Super fast.
Okay. That makes a lot of sense for the unique element case. Pretty neat.
It is. But now let's add complexity. What if the array can have duplicate values?
Right. The second scenario from our source material.
The overall goal is the same. Insert the target while keeping the array sorted. But there's a new rule for duplicates.
Let me guess. If the target value already exists multiple times.
Then the new target must be inserted at the leftmost possible position among those existing duplicates.
Ah, okay. Not just any of the duplicate spots, but the very first one.
Exactly. This is a pretty common requirement, actually. You often want the first available slot or the beginning of a block of identical items.
So a standard binary search might find a 5-foot if you're looking for 5, but maybe not the first 5 if there are several.
Right. It might land you somewhere in the middle of a block of 5s.
I suppose you could just find any instance with binary search and then, I don't know, scan backwards from there, step left, until you find something that isn't a 5.
You could. The source mentions that possibility, but think about the efficiency.
Yeah, that scan could be slow. If you have, like, a million 5s at the start of the array.
Exactly. That linear scan backwards could take ON time in the worst case. It kind of defeats the whole purpose of using binary search in the first place.
Right. We want to stick with that O log n efficiency if possible. So how do we tweak binary search to directly find that leftmost boundary?
Okay, the core structure stays the same. We still have our closed interval ij, we still loop while ij, we still calculate the midpoint m.
Okay.
The key difference lies in how we adjust the pointers based on the comparison, specifically when num-ism is equal to the target.
Ah, that's the critical moment then. Walk us through the logic.
Sure. First case. If num-ism is strictly less than the target.
Same as before, right. Target must be to the right.
Exactly the same. Everything at m and to its left is too small. So we move I to m+1. New range m+1, j. No change there.
Okay, got it.
Now, the crucial part. If num-ism is greater than OR equal to the target, we group these two possibilities together now.
Greater than OR equal 2, why group them?
Think about our goal. Find the leftmost position. If num-ism is greater than the target, we definitely know the target, and its leftmost position must be to the left of m. So we need to search in I, m1.
Okay, that makes sense.
Now, if num-ism is equal to the target, this could be the leftmost one we're looking for. But maybe there's another target element even further to the left.
Right, we can't just stop here like we did in the unique case.
We can't. To find the absolute leftmost one, we need to keep searching in the left subarray. So even when num-ism equals the target, we treat it as a reason to potentially move our right boundary further left.
So in both cases, num-ism of target and num-ism as target, we do the same thing.
Yes. In both cases, we know the leftmost possible position is either at m or somewhere to its left. We must continue searching in that direction. So we move the right pointer, j, down to m1.
Gray area? M1.
Correct. Our new search range becomes I, m1.
Huh. So, by moving J to M1, even when we find an equal element, we're basically saying, okay, maybe M is it, but I'm going to keep looking left just in case there's an earlier one. We don't commit to M yet.
That's exactly it. You're ensuring that you don't prematurely stop at an occurrence. You force the search to continue exploring the left side, effectively pushing I towards the true leftmost boundary. J keeps getting pulled left of any potential candidate
Right.
until I is forced into the first valid spot.
Okay, I think I see how that subtle change works. It keeps the pressure on finding the earliest possible index
Precisely. So the loop I continues.
until I becomes greater than J again.
Right. And when that loop terminates, what does I represent this time?
Well, following the logic, I got pushed past everything strictly less than the target, and J got pulled back past everything greater than or equal to the target. That wasn't the final leftmost one. So how should it end up?
At the index of the first element in the array that is greater than or equal to the target,
Just like before.
just like before. But because of how we handled the equality, JM11, if the target was present, I will have been nudged along until it lands precisely on the index of the very first occurrence of that target.
And if the target wasn't present at all?
Then it still lands on the correct index, where it should be inserted to maintain sorted order, same as the unique case. The logic finds the boundary correctly, whether the target exists or not.
Let's do that quick trace again to lock it in. All right, 2, 5, 5, 7. Target.
Okay, N4. Initial I0, J3.
Midpoint M was 0 plus 3, 2, 2, O's 1. Nums 1 is 5. That's equal to target.
Right, and in this version, num says on target means we move J. So J becomes M1, which is 1, 1 is 0.
Okay. New range I, J is 0, 0, 0. Loop continues since I, J.
Midpoint M, 0 plus 0, 2 ED0, 0. Num 0 is 2.
2 is less than target 5, so numism target.
Which means we move II becomes M plus 1, which is 0 plus 1 equals 1.
Okay. New range I, J is now 1, 0.
And now I, which is 1, is greater than J, which is 0.
So the loop terminates.
And the value of I we return is 1.
And looking back at 2, 5, 5, 7, index 1 is the index of the leftmost 5. It worked.
Yep. That trace shows how moving J left on equality forced I to settle at the start of the 5 block.
That's really clever. Such a small change in the logic. J, M1 instead of stopping or moving I makes it find that specific boundary.
It really highlights the power and subtlety of these algorithms.
Yeah.
The core OLOG and efficiency is maintained,
Hmm.
but we get this specific leftmost behavior.
So let's tie this all together. We started with basic binary search for just finding things.
Right.
Then we adapted it to find an insertion point in a sorted array with unique elements.
Handling the target found versus target not found cases using the pointers I and J.
And then we tweaked it again, just slightly, to handle duplicates and specifically find the leftmost insertion point.
That crucial change being how we handle the numism target comparison. We keep searching left by moving J.
It all comes down to how you manipulate those I and J pointers to shrink the search space strategically based on the comparison at the midpoint M.
That's the essence of it. Discarding half the possibilities at each step is what gives binary search its logarithmic speed. The specific rules for moving I and J just tailor which half you discard to suit the problem, finding any instance, finding the first instance, or just finding the insertion slot.
And you mentioned the source uses that closed interval IJ. I know sometimes people use like IJ, where J is one past the end.
Yeah, that's another common convention, left closed, right open. The pointer updates and loop conditions change slightly if you use that interval definition, but the fundamental binary search idea having the space is exactly the same. You can achieve the same results.
Good to know. The underlying principle is robust.
Very versatile.
Okay, so wrapping up this deep dive, we've really seen how binary search is much more than just a simple search tool. It's a foundational technique for efficiently maintaining sorted data.
Absolutely. By understanding how to use it to find insertion points, you gain a powerful tool for keeping data structures ordered without resorting to slow linear operations.
We saw the difference between handling unique items and finding that specific leftmost spot when duplicates are involved.
And that difference really just came down to that one critical logic change when numsism equaled the target.
Yeah, understanding these adaptations, it's not just academic, is it? It feels like a really good example of computational thinking.
It really is. You take a core algorithm, binary search, and you make these small, smart tweaks to solve related problems like insertion or boundary finding with that same amazing efficiency. That's how you build faster, more scalable software.
And thinking about that, we focused on finding the leftmost occurrence or insertion point by adjusting how J moved when numism was equal to the target. That kind of makes you wonder, could you make a similar but different tweak to find the rightmost occurrence of an element? If you wanted to insert something just after a block of duplicates, for instance.
That's an excellent question to ponder. If moving J left helped find the left boundary, what might moving I differently do?
Hmm. And maybe there are other boundary finding problems too, like find the first element that's strictly greater than the target, or the last element strictly less.
Exactly. Once you grasp how manipulating I and J controls the search boundary, you start seeing how binary search can be adapted for all sorts of problems beyond simple existence checks. It's a really fundamental pattern in computer science.
Definitely something for our listeners to think about as they encounter more algorithms and data structures. How can this core idea of binary search be applied in new ways?